everyone, welcome to our last and final video in this Visualizing and Summarizing Data series. Let's talk about some of these numerical summaries that we've been seeing. Some of them will be ones that are familiar to you. So for example, we can measure the center of a variable with something like the mean or the median. So for example, the sample mean is just the average of all individual observations in the sample. So we take our observations for the variable, add them all up, divide by the number of observations. In this class, we'll denote that sample mean with an X bar. Another useful measure of center for us when we're describing a variable is the median. Take all the observations, order them from smallest to largest, pick out the middle. There's the median. So for example, let's find the mean and median age of ICU patients in this sample. Now fortunately the code here is hidden because I want to talk a little bit about the relationship here between the mean and the median. So I'd like to focus on that. So we've got the mean age, which is 57.545. We've got the median age, which is 63. The median's a little bit higher than the mean. Does the average age of patients admitted change with admission type? So now we've got a two-way table here. R often calls data sets tables, especially if they're coming from the tidyverse. So table is just another word for a data set or a table. So we have our type, elective versus emergency. The mean for the elective patients is about 64. Mean for the emergency patients is about 55. Median 68 versus 60. In both cases, the elective patients tended to be a little bit older, which means that patients who are coming into the ICU from an elective procedure tend to be older. Those elective procedures are planned ahead of time, so it should make sense that older patients are more likely to have those ahead of time procedures planned. So let's find the range and quartiles of age and talk a little bit about how spread out the ages are. What you're seeing here is the output of another very useful function for us. This is something called the favstats function that produces this. You'll see this a lot throughout the semester. Again, I just want to focus on the output for now, so we'll worry about the code a little bit later. So first, let's find the range and the quartiles of the age. So range, something you've probably learned about before, the maximum observation minus the minimum observation. So for us, the maximum is 92, the minimum is 16, so the range is going to be about 76. There's a 76-year gap between the youngest and the oldest patient. Now, how spread out are the ages? The range tells us that difference, but it doesn't really tell us about the variation in the middle of the data. Here's what this code actually looks like, by the way, to calculate all of these. We are looking at the favstats function here. Notationally, we're going to take this function from the mosaic library. Our favstats function is going to calculate our favorite statistics. The tilde indicates the variable that we're interested in, so tilde age, data equals ICU admissions. Now, this is going to be one downside of working with R. R is what's called an open source programming language, which means that anyone can write R functions, can contribute R code, can make changes, and make it available for others to use. Because of that, the syntax is not always the same. So you're going to see syntax vary from function to function and library to library. This is another one of those reasons why I suggest copy, paste, change as you're working with code, especially initially. Now, let's point out one of these statistics, SD. That might be something new for you. It's an incredibly useful summary statistic called the standard deviation. So the sample standard deviation is a measure of the variation of a data set. What it tells us is really the typical or the usual distance between an individual observation and the sample mean. So how far a typical observation falls from the average. We calculate this by taking the sum of the individual observations, xi, minus the mean, x bar, squaring that up, adding them up, divided by n minus 1, all of that in the square root. This is definitely one of those formulas that we won't be calculating by hand this semester. The interpretation of this, what does this mean? Well, data sets or variables with large standard deviations tend to be pretty spread out. The observations tend to be pretty far from the mean. Whereas if that standard deviation is pretty small, that tells you that the observations are typically very close to the mean. Why are we using n minus 1 here? This is something that you might see in your textbook or see online. It is kind of a weird distinction. Here's the reason why we do this. Dividing by n minus 1 makes the sample standard deviation what's called an unbiased estimate. That means that this formula gets as close as we can to estimating the true standard deviation of a population, which we will call sigma. So if you wonder why we're dividing by n minus 1, it's just to get a more accurate picture of the standard deviation. There's another term for variability that you'll often see floating around, and that's called the variance. The variance actually just turns out to be the standard deviation squared. So if you've got the standard deviation, you can calculate the variance. The variance has some really nice mathematical properties. However, talking about the squared distance between an observation and a mean isn't as useful in practice when you're describing a data set. So we'll refer to the standard deviation as a useful measure of variability. So, for example, what can we say about the variability of ICU patients at this hospital? Well, we can say that the typical ICU patient is within about 20 years from the mean. So most ICU patients in this data set are going to be between about the mean minus the standard deviation, so about 37 and about 77 years old. That's where we will expect most of our patients to fall. Does the variation change depending on admission type? Yeah, a little bit. The standard deviation of elective patients is about 15 years. The standard deviation of emergency patients is about 21 years. So the emergency patients are a bit more spread out in terms of the ages that we would expect to see. Looking at the two histograms side by side here, we can see that sort of carry through. The elective patients tend to be more concentrated in this 50 to 75 range. The emergency patients are a bit more spread out throughout the range, so there is some higher variability, a higher standard deviation. Now, the last thing that I want to talk about is working with two categorical variables in this video. A table that contains counts or the number of observations that fall into different categorical variables is a contingency table. So we have one variable on the rows, one variable on the column. Within the table, we have the counts. Another term for these are two-way tables. So let's say we want to know whether or not patients with a history of cancer are more likely to be admitted as emergency patients. Well, we could take a look at the cancer history, so yes or no, type of admission, and then we can see, well, how many fall into each of these. Our contingency table usually looks like this. So this is probably the form that you're used to seeing with these tables. We have cancer status, no, yes, elective, yes, emergency. Here's how we can produce a table like this. So we'll take the ICU admissions data set. We'll group it based on two variables, cancer and type. Summarize n equals n. If we just stopped here, so if we ignored this yellow line, we would get a table like this. By adding this spread, what we're doing is taking the type and we're spreading it out. So 4 lines of code to produce this table. There are lots of different ways to accomplish the same thing, and that's true in any programming language. That's especially true in R. Some will be easy, some will be hard. So another way to produce a two-way table such as this is to use the tally function from the mosaic library, tally up how cancer changes depending on type, or cancer, this vertical bar you can read as split by type. Both notations or both functions will produce the same output. Now let's talk about plotting this categorical data. We can plot it in what's called a stacked bar chart. So for example, we have cancer on the x-axis, no versus yes. The shading of the bars represents the type of admission. So for the cancer patients, they most often were admitted following elective or planned procedures. For the no cancer patients, they most often were admitted following emergency procedures. We could use, say, a facet to split this graph up into multiple charts. Or we could add position equals dodge. We could dodge the bars, make them stand next to each other rather than stacking them on top. There is a lot that we can do. There are tons of different ways to visualize data, some more effective than others. Throughout this week, so in class both days, we're going to take a look at a couple different data sets and just practice making visualizations, calculating summary statistics, and interpreting them. So we will do a lot of work with this in order to get you all comfortable working with R in RStudio. It doesn't come right away. This is hard. That's okay. You'll also get a lot of sample code to use. I'm not going to throw you guys in right away. We'll start with full code. We'll take away some variables. We'll take away a little bit at a time to get you guys used to this. So that is it for our Lecture 4 series, or our very extended Lecture 4 series. I'll see you guys in class this week or in the next video. Take care.